Right now, inside a lab somewhere in the United States, a team of engineers is assembling something that has never existed before in the history of the universe. Not a chip in any sense you'd recognize, not a circuit board. It looks more like a chandelier, copper rings hanging from a ceiling, nested inside each other, descending toward a single point. And at that point, at the very bottom, sits a piece of metal smaller than your thumbnail. That thumbnail is why every major government on Earth is spending billions of dollars. That thumbnail is why IBM, Google, and Microsoft are locked in the most expensive technological arms race since the space program. And that thumbnail, if the physics holds, will eventually make today's most powerful supercomputers look like pocket calculators. This is not a video about what quantum computers can do. Plenty of people have made that video. This is about something nobody actually explains. How you physically build one, step by step, from raw material to finished machine. And the answer involves a metal that conducts electricity with zero resistance, a refrigerator colder than deep space, hundreds of cables that can't carry a single stray photon, a particle predicted in 1937 by a physicist who then mysteriously vanished, and a verification problem so deep that even the people building these machines haven't fully solved it. Let's start at the very beginning. Before you design a single circuit, before you order the fridge, before you write a single line of software, you have to choose the right material. And the material at the heart of almost every leading quantum computer is one of the strangest substances in physics. It's called a superconductor. At room temperature, it looks and behaves like an ordinary metal, such as aluminum or niobium, depending on the design. But cool it below a critical threshold. For aluminum, that's around 1.2 Kelvin, roughly 272 degrees below zero, and something genuinely bizarre happens. Electrical resistance doesn't decrease. It doesn't approach zero. It becomes exactly zero, completely, permanently, as long as the temperature holds. At these temperatures, electrons that normally repel each other begin to form coordinated quantum pairs called Cooper pairs, named after Leon Cooper, who shared the Nobel Prize in Physics in 1972 for explaining the phenomenon. These pairs move through the material in lockstep, governed by a single shared quantum wave function. The whole system behaves as one quantum object, and this is what makes a qubit possible. IBM, Google, and most of the industry build their quantum processor chips from circuits of aluminum and niobium deposited onto a wafer of silicon or sapphire. The circuits are etched using photolithography, the same fundamental technique used to make classical chips, but with one critical difference. The geometry of each circuit has to be controlled to nanometer precision, because the exact shape determines the qubit's resonant frequency, usually somewhere between 4 to 8 gigahertz. That's microwave range. Each qubit is essentially a tiny loop of superconducting wire, with a weak link interrupting it, a structure called a Josephson junction. This junction is a sandwich of superconductor, insulator, and superconductor, just a few nanometers thick. Brian Josephson predicted its behavior theoretically in 1962 and received his own Nobel Prize in 1973. The junction is what gives the circuit its non-linear quantum character, what separates it from any classical electrical circuit. The finished chip is almost comically underwhelming to look at. Google's Willow processor, announced in December 2024, fits 105 qubits onto a chip roughly the size of a thumbnail. IBM's Condor processor, unveiled in December 2023, fits 1,121 qubits onto something you could cover with your palm. The entire future of quantum computing, at this moment in history, lives on circuits thinner than a strand of DNA, etched onto pieces of metal smaller than a playing card. But here's the problem, and it's a problem so serious that it completely defines every engineering decision that follows. That chip, sitting on your desk at room temperature, is completely useless. Worse than useless, because at room temperature, the quantum states that make a qubit powerful don't survive. They can't. The universe won't allow it. To understand why, you need to understand something called decoherence. A qubit's power comes from superposition, the ability to exist as 0 and 1 simultaneously, to hold multiple states at once, to process possibilities in parallel in a way that no classical bit can. But this quantum state is extraordinarily fragile. Any interaction with the outside world, a stray electromagnetic wave, a vibration from a passing truck outside the building, a cosmic ray that spent 1 billion years traveling across the galaxy only to arrive at your lab ceiling at exactly the wrong microsecond. Any of these things can cause the quantum state to collapse. The qubit snaps into a definite value. The calculation is ruined. This collapse is called decoherence, and managing it is, without exaggeration, the central engineering challenge of the entire field. Here's the scale of the problem. Google's Willow chip, the most advanced commercially relevant quantum processor on the planet as of late 2024, has qubits that hold their quantum state for approximately 100 microseconds. That is 1/10,000th of a second. In specialized research settings, Fermilab's SQMS Center has pushed superconducting qubit coherence to 0.6 of a millisecond. Aalto University in Finland reached 1 full millisecond in July of 2025. Princeton reported 1.6 milliseconds in November 2025. These are world records, and they are still measured in fractions of a second. Every single physical design decision in building a quantum computer flows from this one fact. The chip must be isolated from thermal noise, electromagnetic interference, vibration, magnetic fields, and ionizing radiation. Earth's magnetic field alone is strong enough to disrupt certain qubit states. Natural radioactivity in the walls of the building can flip a qubit. IBM builds its quantum data centers on vibration-isolated foundations. The fridges are wrapped in multiple layers of specialized magnetic shielding. Every signal line entering the system is threaded through infrared filters, attenuators, and one-way microwave valves called circulators to prevent room temperature noise from riding the cables down to the chip. A human breath directed at a qubit chip would crash the computation. What you're really building, when you build a quantum computer, is the most elaborate noise cancellation system in the history of engineering. And then you put the actual computer inside it. So you have a chip. You know what you're fighting. Now comes the step that genuinely sounds impossible. To make that chip work, you have to cool it to a temperature that does not naturally exist anywhere in the observable universe. And you have to do it inside your lab. Every single time you want to run a computation, superconducting qubits must operate at around 10 to 20 millikelvin. That is 0.015 degrees above absolute zero, the theoretical minimum temperature that the laws of thermodynamics allow to exist. For comparison, the average temperature of empty space between galaxies is 2.7 Kelvin. The inside of a running quantum computer is roughly 150 to 270 times colder than that. When IBM or Google runs a quantum algorithm, the chip at the bottom of their refrigerator is, at that moment, the coldest object in the known universe. Colder than any star. Colder than any nebula. Colder than the void between galaxy clusters. The machine that achieves this is called a dilution refrigerator. It costs between $500,000 and over $3 million. It works by exploiting the quantum mechanical behavior of two isotopes of helium. Helium-3 and helium-4. When these two isotopes are mixed together at extreme cold, helium-3 spontaneously dissolves into helium-4, and this process absorbs heat. It's a continuous endothermic reaction, a chemical act of constant absorption that bleeds thermal energy out of the system, stage by stage, layer by layer. The dilution refrigerator has 5 distinct temperature stages. At the top, room temperature, around 300 Kelvin, that's where the classical control electronics live. Below that, a 4 Kelvin stage cooled by a pulse tube cryocooler running on compressed helium. Then the still at around 700 millikelvin, where the dilution process begins. Then the cold plate at around 100 millikelvin. And finally, at the very bottom, the mixing chamber, 10 to 20 millikelvin, where the quantum processor chip is mounted. The device hangs from the ceiling of its housing like an inverted wedding cake. Concentric copper rings, each one a colder layer than the one above it, descending toward the chip at the center. This is the chandelier shape you see in every photograph of a quantum computing lab. It takes between 48 and 72 hours to cool from room temperature to operating temperature. Any significant disturbance during that window, a power fluctuation, a seismic event, someone slamming a door too hard, and you start the whole process over. But getting cold is only half the problem, because now you need to talk to a chip that is sitting at 15 millikelvin, and you are sitting at room temperature. And those two facts create one of the nastiest engineering problems in physics. How do you send instructions to a machine that lives at near absolute zero without warming it up? The answer is coaxial cables, hundreds of them, threading down through every temperature stage of the dilution refrigerator. Each qubit needs its own dedicated line for control signals and a separate line for readout. IBM's largest processors require thousands of signal lines running through a single cryostat. Every cable has to be thermally anchored at each temperature stage to bleed off the heat it carries from above, and filtered with attenuators to prevent room temperature microwave noise from reaching the chip. A room temperature signal carries roughly 10 to the power of 20 times more thermal energy than is acceptable at the chip. Closing that gap requires extreme filtration at every stage. The control signals themselves are microwave pulses generated by classical electronics at room temperature. For a superconducting qubit, a single gate operation lasts about 20 to 50 nanoseconds, and must be shaped to match the qubit's resonant frequency within kilohertz accuracy. Different pulse shapes correspond to different quantum gate operations. Reading the result works in reverse. A low power tone goes down to a resonator coupled to the qubit. The resonator shifts its frequency depending on the qubit's state, and classical computers decode the return signal. This wiring bottleneck is one of the hardest limits on scaling. Every qubit needs its own room temperature control hardware. Scaling to 1 million qubits under current designs means a control rack the size of a warehouse. Companies including IBM and Intel are working on cryogenic control chips that operate at 4 Kelvin inside the fridge itself to drastically reduce these requirements. This problem does not yet have a clean solution. Now, you have a chip, you've cooled it, you're talking to it, and it is still making errors constantly, randomly, unavoidably. The best 2-qubit gates on leading quantum processors today achieve about 99.5% fidelity. That sounds excellent. It is not. If every gate has a 0.5% chance of error, and a useful algorithm requires millions of gates, the output is noise. This is why quantum error correction is not a feature of quantum computers. It is the entire engineering project. The insight behind quantum error correction is counterintuitive enough to deserve a moment. You cannot copy a qubit. This is a fundamental law of quantum mechanics called the no-cloning theorem. So you cannot check your work by making a backup the way you would with a classical system. Instead, you encode the information of one logical qubit across many physical qubits, and you continuously measure the relationships between those physical qubits. Not their actual states, but whether they agree or disagree with each other. Disagreements reveal errors. You correct the errors without ever reading the logical qubit directly. You are watching the shadows on the wall without looking at the light source itself. The most widely used scheme is the surface code, a two-dimensional grid of qubits where data qubits hold information, and ancilla qubits constantly check their neighbors for disagreements. The larger the grid, the better the protection, provided the underlying error rate is below a critical threshold. In December of 2024, Google's Willow chip provided the first experimental proof that this threshold can be crossed at scale. As they increased the surface code grid size, the logical error rate dropped exponentially. Not slightly. Exponentially. This was the result the field had been waiting for since Peter Shor first proposed quantum error correction in 1995, 30 years between the theory and its validation in real hardware. The overhead remains steep. One reliable logical qubit currently requires roughly 1,000 physical qubits. Running Shor's algorithm to break standard 2048-bit encryption requires somewhere between 1 million and 4 million physical qubits. Current machines have hundreds to low thousands. That gap is the engineering project of the decade. So that's the superconducting path, the one IBM and Google are on. But there are 3 other serious approaches to building a quantum computer, and none of them use superconductors at all. Trapped ion quantum computers, built by companies like IonQ and Quantinuum, use individual atoms suspended in midair using electromagnetic fields inside a vacuum chamber. No chip, no Josephson junction, no dilution refrigerator. Laser pulses manipulate the electron energy states of the ions, which serve as 0 and 1. These systems achieve some of the highest gate fidelities and longest coherence times of any qubit type. The trade-off: gate operations are roughly 100 times slower than superconducting systems. Neutral atom quantum computers, built by companies like Qubit and Atom Computing, go a step further. The atoms aren't ionized, they're neutral, held in place by tightly focused laser beams called optical tweezers. The crucial advantage: atoms can be physically moved and repositioned mid-computation, allowing 2-qubit gates between any pair of atoms regardless of their starting positions. Superconducting chips have fixed connectivity. Qubits can only directly interact with physical neighbors. Neutral atom systems don't have that constraint. In 2025, Qubit delivered a 37 logical qubit system built from 260 physical qubits to Japan's National Laboratory, the most logical qubits delivered to any customer in the history of the industry. And then there's the fourth approach, the one that Microsoft spent nearly 20 years and a reported investment exceeding $1 billion pursuing. A quantum qubit made from a particle that, for most of that time, hadn't even been definitively observed. In 1937, Italian physicist Ettore Majorana published a theoretical paper predicting a particle that is its own anti-particle, a fermion that is indistinguishable from its own mirror image. The following year, Majorana boarded a boat traveling between Palermo and Naples and disappeared. No body was ever found. The particle bearing his name went undetected in any controllable way for nearly 90 years. On February 19th, 2025, Microsoft unveiled the Majorana 1 chip. It contains 8 qubits built around Majorana 0 modes, quasi-particles that appear at the ends of specially engineered nanowires, made from indium arsenide coated with aluminum, cooled to near absolute zero and tuned with a precisely calibrated magnetic field. The nanowire enters a state called topological superconductivity. Majorana 0 modes appear at each end, and the two endpoints together form a single qubit. The reason this matters, and the reason Microsoft made a 2-decade bet on it, is that a conventional qubit stores information in a single localized physical location, easy for the environment to find and disrupt. A Majorana-based qubit stores information non-locally, distributed across the structure of the system. The information isn't in any one place. Noise can't easily destroy what it can't locate. Microsoft claims this topological protection makes the architecture scalable to 1 million qubits on a chip the size of your palm. Independent scientific verification of the full topological qubit claim is ongoing. But the engineering infrastructure is real, and if the physics holds, it changes every calculation about how many physical qubits you need to build a useful machine. So you have a machine. You've chosen your qubit type. You've cooled it, wired it, built the error correction. Now you run a computation. And here's the question that almost nobody stops to ask. If a quantum computer gives you an answer that no classical computer could have calculated, how do you know the answer is right? This is not trivial. You built the machine specifically because classical computers can't check its work, but that means you can't check its work either. The field has developed several strategies. Randomized benchmarking runs known circuits to characterize error rates statistically. Cross-entropy benchmarking compares the quantum output distribution against classical simulations of small subsections of the circuit. For practical problems, the approach is to run algorithms where the answer can be partially verified, optimization problems where you can confirm a solution is valid, or physical simulations where results can be compared against laboratory measurements. In October of 2025, Google published results for an algorithm called quantum echoes. The calculation ran 13,000 times faster on Willow than the best classical algorithm on a state-of-the-art supercomputer, and it was verified against known theoretical predictions from condensed matter physics. The computer was fast, and it was provably right. Most researchers considered this the first credible demonstration of quantum advantage on a task with genuine scientific meaning. That brings us to where we are now, and where we are going. The United Nations designated 2025 the International Year of Quantum Science and Technology. Google's roadmap targets a long-lived logical qubit by 2026 and full fault-tolerant quantum computing by 2029. IBM's quantum Starling system, also planned for 2029, aims for 200 logical qubits executing 100 million error-corrected gate operations. The threshold most physicists identify as the point where quantum computers become genuinely useful for real chemistry and materials problems. Amazon entered quantum hardware development directly in February 2025 with the Ocelot chip, claiming 90% reduction in error correction overhead. Quera targets 1,000 logical qubits by the early 2030s. And somewhere in this decade, the same machine being built to simulate molecules will also be capable of running Shor's algorithm at scale. In August of 2024, the National Institute of Standards and Technology finalized the first 3 post-quantum cryptography standards, encryption algorithms designed to remain secure against quantum attacks. Transitioning government and enterprise networks to these standards is expected to take a decade or more. The quantum computer that could break current encryption and the defenses designed to stop it are being developed in parallel, often by the same institutions. We are not yet in the ERA of quantum computers. We are in the ERA of building toward them, and the distance is measured in years, not decades. The Wright brothers' flyer at Kitty Hawk in 1903 flew for 12 seconds, by almost any measure, barely useful. But the physics was proven. The engineering trajectory was clear. 20 years later, Charles Lindbergh crossed the Atlantic. The machines being assembled right now, in refrigerators colder than deep space, on chips smaller than your thumbnail, behind layers of shielding that block out the entire electromagnetic universe, these are the 12-second flight. The question isn't whether they'll cross the Atlantic, it's what ocean they're going to choose. Somewhere right now, at 15 millikelvin, 150 times colder than the void between the stars, a qubit is in superposition. The material was grown atom by atom. The junction was etched to nanometer precision. The signal traveled through 300 Kelvin of temperature difference without warming the chip by a single measurable degree. And now it is sitting at the edge of 0 and 1, holding both at once, waiting for the measurement that will collapse it into an answer. We built the fridge, we built the chip, we built the wires and the shields and the error correction. We built the whole impossible machine. And now we wait to hear what the universe has to say.